Okay. So these things will be mentioned with the first bit will be A naught, B naught, second bit will be A1, B1, and so on and so forth. How many number of bits are there with you? So you can able to so subscript with those particular values there. Then how could you construct? What is the way of construction of so multi-bit so adder here in the sense multi-bit adder will be done something like this here. So it will be constructed. So something seems like this here. So for example, we are trying to construct for only 4-bit 4-bit adder. So let me say first one is this one is a full adder, 0th bit full adder. Here it is full adder. This is another full adder. So if you do have as much as many, so let me draw, let me copy and paste for several times. How many number of bits are there with you? Those number of bits are supposed to be taken into consideration here. And this is one more full adder, and this one more. This is one more full adder. One more full adder. 4-bit full adder. Let me consider 4-bit full adder will be there with me. Okay. For every 4-bit, so I do have this is full adder naught, this is full adder 1, this is full adder 2, and this is full adder 3. So I do have 2 inputs are there with me for every full adder. Of course, 3 inputs are there with us. So one is so A naught and B naught. This is the first one, and of course C naught will be always so C naught also will be there with us. And here it is. So A1 and this will be B1. Okay, 1, and this will be A2 and B2. So B2, and this is A3, and here it is B3 here, B3. Now, so one carry has already given to first full adder here. So the outcome of this particular full adder, whatever the outcome, so outcome of this full adder will be first one is sum naught, first bit sum. So this one is sum 1, and this one is sum 2, and this one will be sum 3. And of course, whatever the outcome of full adder, second outcome is there with you, that second outcome will be the carry. Whatever the carry you got, that particular obtained carry will be, so carry will be input of second full adder, and this outcome carry will be input of so next one, that is C2, and this will be so outcome of this particular FA2 will be so C3 here, and final outcome will be your actual so carry here. This is C4. Okay, and very important thing you need to remember while constructing this particular thing is always C naught must be equal to 0. Always C naught must be equal to 0. It must be always equal to 0. Now you can see, for example, I'd like to add these two. I'd like to add so 1 0 1 1. So this will be A, and B will be equal to so 0 1 1 1. So these are the two values which I would like to add here. If I would like to add these two, so 1 plus 1. So on the so third input for this particular thing will be always C naught will be equal to 0. So let me consider this is carry. Always C naught will be equal to 0. So 1 plus 1 will be 0, and carry is 1 here. So let me operate everything here in terms of this one. So here it is 1, here it is 1, and of course next input will be 0 here. And here it is 1, and here also 1 as far as second bit position. And the third bit position is A is 0 and B equal to 1. A2 equal to 0 and B2 will be equal to so 1 here. And second one, this one, third bit will be, I mean fourth bit will be, this is 1 and this is 0, this is 1 and this is 0. Let us execute this one for a while. So 1 plus 1, that is 0. 0 is the carry. Let me operate a carry here. Let me operate the carry here, and 1 will be the outcome here. 1 will be the outcome here. Okay. So sorry, I wrote something wrong. So 1 plus 1 will be, so sum equal to 0 and the carry will be equal to 1 here. So now if you take a second full adder FA1, full adder 1 will be taken, 1 plus 1 will be equal to 0 with carry 1. So 0 plus 1 will be equal to 1 and the carry will be equal to 1 again here. And then here, so 1 plus 0 plus 1 will be 1, 1 plus 1 will be sum is 0 and the carry will be 1 here. And now, so if you consider, so here it is 0 plus 1, that is 1, 1 plus the 1 will be sum is 0 and the carry is 1 here. So finally your outcome will be seen something like this here, 10010. This is the outcome. If you do the operation here as well, so manually if you do the operation, it would also be same. That is, so here it is 1, so here it is 1 here it is 0. So sorry, not 0, 1 here, sorry, 1 here. So 1 plus 1, here it is 0, here it is 1, here it is 0, and this 2 carry will be this one. So this is the outcome of this one, of course the same outcome. So if a number of bits will be available more and more, you have to add the full adders as much as many as far as your input bits will be considered here. So this is for 4 bits. If you have 6 bits, yes, you can add 2 more full adders. If you have 8 bits, if you have, so 4 more full adders. If you have 10 bits, so 6 more full adders you can add in the circuit. If you add in the circuit, so you could get, so everything will be in a proper way. This is the way you can perform, so 4-bit full adder. Okay, 4-bit full adder here. So finally, as a conclusion, in terms of adders, as a conclusion in terms of adders, so look at this in terms of adders. So if you want to add 2 bits, exclusively 2 bits, then you need half adder. So let me turn off to the top. So if you want to add only 2 bits, something like this, if you want to add only 2 bits, something like this, so then you required half adder. Half adder will be seen something like this. If you want to add 3 bits, you need full adder. Full adder will be seen something like this, and this is the logic diagram for full adder. That is the logic diagram for full adder. And if you want to perform more than, so 2 bits or 3 bits, some sequential number of bits are there, something like this. If you are trying to add more number of bits, something like this, so you'd like to take a multi-bit adder. This is multi-bit adder. Okay, so input A might be having several bits, input B might be having several bits, then you may be add something like this here. Within this multi-bit adder, you must remember one thing, so that is C0, input C0 for first full adder must always equal to 0, must always equal to 0. It must be always equal to 0. That's what you need to consider. So these are different kinds of adders which are available for us in so computer organization here. Okay, then considering that if subtraction, some kind of subtraction will be gets happen, for example, some kind of subtraction can be gets happen here, how could you do that? So probably that is not there in our syllabus. I think that is not there in our syllabus. Oh, directly they have gone for multiplexers. Directly they have gone for multiplexers. So even then there is a possibility to ask some kind of question that, so 4-bit adder subtractor, something like that they will ask you. 4-bit adder subtractor will be gets, so it could be so done both addition and subtraction as well. Addition and subtraction as well. If you want to perform such kind of operation, so what is the logic diagram you are supposed to so draw there? What is the logic diagram you are supposed to draw there? So that is what the point. So normally if you are trying to perform subtraction, so what kind of activity you are supposed to do there here in the sense, wanted to perform subtraction operation. So normally, so minute is supposed to be converted into 2's complement and then add to that particular 2's complement value to the subtrahend. So subtrahend is converted into so 2's complement and add that subtrahend to the minute, then so that will be considered as subtraction. And there are certain number of rules and regulations. Let me give you what are those rules and regulations here. So let me take so one or two examples. Then numerical examples. Then I'd like to explain what exactly the 4-bit adder or subtractor here. How subtractor is going to be constructed. Let me give you in such a way that. So, for example, if you are supposed to perform this particular operation, so let me take one particular thing here. So minute will be equal to, for example, 10110. Okay. Subtrahend will be equal to so 01101. So this is the subtrahend, and you must subtract some from minute. So you have to subtract this particular value. So here in the sense minus in the sense, if you want to perform this operation here in the sense, directly subtraction operation cannot be done. So addition is very simple than subtraction here. Addition is very simple when we compare to the subtraction value here. So therefore, so to perform this particular subtraction operation, we would like to consider something seems like this. Whatever the subtrahend you are having with you, so convert that subtrahend into so it's equivalent to 2's complement. First of all, you need to convert that particular operation, that particular value into its equivalent 2's complement value. After getting the 2's complement value, then that particular 2's complement must be added to the minute. Then whatever the value you got, that particular value could be considered as so the outcome here. So how you can do this particular operation here? How you can perform the same kind of operation here? Let me give you one example here, then you could understand very easily. So 2's complement of this subtrahend will be so 1's complement of this particular 1's complement of s will be equal to flip the bit. So from 0 to 1 and 1 to 0. So here, so 1's complement will be here it is 0 and here it is 1 and here it is 0, here it is 0 and finally this is 1. After getting 1's complement, if you add plus 1, that will be considered as 2's complement here. So add plus 1 here, then it will be considered as 2's complement here. So this is 1, this is 1, this is 0, this is 0 and this is 1 here. Okay. So after getting this 2's complement value of the subtrahend, add this value to the minute. So 10110. So add a 2's complement form of subtrahend, that is 100. So 1 1 I think. So this one. Add this particular thing here. If you add these two, so 0 plus 1, so 1. 1 plus 1, 0 with carry 1. 1 plus 1, 0 with carry 1. 1 plus 0 plus 0 will be equal to 1. 1 plus 1, 0 with carry 1. And of course, it is carry. While doing this particular operation, what we are supposed to understand here in the sense, whatever the value you got here, whatever the value you got as a subtraction, if this value will be, whatever the value here, subtracted, extra carry will be equal to 1, excluding that particular value, remaining thing will be the actual answer. If extra carry will be equal to 1, so if carry will be equal to 1, excluding this particular one, omit this particular one, and remaining thing will be the answer. If so carry will be equal to 0, then what exactly we are trying to perform here in the sense, you need to convert excluding this particular carry. Here it will be 0 will be get sucked, for example. So excluding this 0, you have to again find the 2's complement of this particular value and put a negative sign. Okay, if it is 0, carry will be equal to 0. So carry will be equal to 0. then excluding that particular carry, remaining value will be again converted into its 2's complement value and add negative sign before that. Negative sign must be preceded. Okay, let me give you one quick example, then you will understand very easily. So for example, if you take these are the biggest values, let me take so some 7. So in terms of 4-bit form, so 7 in the sense 0 1 1 1, and 9 minus 9 will be taken, so 9 will be 1 0 0 1 here. So directly directly we don't have any so particular value here, so therefore you'd like to perform the operation something like this. So 2's complement of this value can be seen like this. So 2's complement will be equal to 0 1 1 1 will be the 2's complement. Okay, 1's complement of so this particular value 1 0 0 1 value, 1's complement will be equal to 1's complement value will be equal to, so this is 0, this is 1, this is 1 and 0, and add 1 here, so you will get 0 1 1 1. So directly I have written as so the 2's complement value of the same here. So something seems like this, something seems like this. Then you got this particular value, then so add to the minute here. So this is my minute, 7 is the minute here, so 0, so 1 1 1. Okay, then so 0, so 1 1 1 can be gets added together here. So 1 plus 1 1 plus 1 0 with carry 1, so triple 1 1 with carry 1, triple 1, so 1 with so carry 1, so 1 here. So what I have given here, so that is something wrong here, wrong notation here. If 1 will be there, then you have to identify the 2's complement, 0 will be there, that is the final answer. Sorry, whatever the discussion I made here, so vice versa, if carry will be equal to 1, the answer will be in 2's complement form. So 0 will be there, carry will be equal to 0, so the answer will be as it is. Okay, here, so carry will be equal to 1, so you must be take so this is this is actual answer. Carry will be 0 in the sense you need to find the 2's complement form and add this one here. So here you can see, so 0 is the carry here, 0 is the carry, because we got 0 as carry. Identify 2's complement of this one, identify 2's complement of this one here. 2's complement of this one will be, so 1's complement will be 0 0 0 1, and add 1 here, add 1 here, 1 plus 1 0, so with carry 1, and here it is 1 0 0, and you have to put negative sign. So look at this, this is the value of 2 in the form of negative. Okay, if carry will be equal to 0, there is no carry with you, so then you have to identify the 2's complement of the resultant value addition, this addition of so minute plus 2's complement of 2's complement of subtrahend, whatever the operation we did here. So you just identify its 2's complement again, excluding 0, you have to identify 2's complement again, and you have to put so what you call this one here, what is that, the negative sign here. Okay, whereas 1 will be there. Let me consider same example, let me consider same example. So 9, same example, I'd like to flip into other way, 9, so that is 1 0 0 1 is the 9 value, minus 7 here, minus 7, that is 0 1 1 1 here. You can see this one here. If you want to perform this particular operation, obviously subtrahend is always trying to convert into its equivalent so 2's complement here. So therefore 2's complement equivalent complement value will be, so seems like this, 1 0 0 0, it is 1's complement of 7, 2's complement will be 1 0 0 1 by adding. So here we have to add 1, so that you could get this particular value. After soon getting this particular value, so this particular 2's complement form of 7 must be added to the 9. So 9 in the sense 1001. So 1001 plus, so 1001. So look at this, 1 plus 1 is 0 with carry 1. So here it is 1, here it is 0. So here it is 0 with carry 1, and of course carry 1. Look at this, what I have told you, if carry will be equal to 1, that is the final answer. Excluding of that carry, so omit this particular carry, don't consider this carry, and remaining thing will be, So positive 2 as the answer here. I hope that you clear. I hope that you got clear. Okay. Subtraction can be gets added together. Then what you need to understand? First, you need to convert. So subtrahend, whatever the subtrahend you can take, convert this one into 2's complement, and the resultant 2's complement value can be added to the minute. Added to the minute. So that is the first operation. Then followed by, after doing so this minute, you need to take care if carry will be equal to 1, on excluding of this particular carry, remaining value will be the final answer with the positive sign. Final answer with the positive sign. Whereas if you are supposed to be perform, so this particular value as 0. So if you got this particular value as 0, so then the value or whatever the answer you could consider here, that answer is in 2's complement form. Again, you need to find the 2's complement. Again, you need to find the 2's complement here. So that is what you need to consider here as far as the points are supposed to be taken into consideration. Now, I hope that you clear. I hope that you clear. Yeah. So how to draw the same? How to draw what you call logic diagram for that? How to draw the logic diagram for the same? So the logic diagram can be drawn something like this here. So you please remember this. Don't I mean, this could not be there in our final examination. Sometimes, as so out of the syllabus, out of the interest of the syllabus, people will ask you this question. People will ask you this question. Don't say that it is not at all in our syllabus, because adders are there. It is our responsibility to explain. So subtractor as well. Adders are there with you. So it is our responsibility to explain subtractor as well. So therefore, I'd like to take the subtractor. So hope that this concept is clear. Now you can see this is our so only positive bit adders. This is only positive bit adders. Now how could you make the subtractor here? So look at this, how subtractor will be there with you, how it could be comes with you. Look at this. How could you identify the 2's complement of this one here? How could you identify the 2's complement with this here? Look at this. If I would have B as the second bit, will be having some kind of 1. How could I make this particular value into 0? How could I make this particular value into 0? Otherwise, B might be having 0. How could I make this particular value into 1? So look at this. How could you do this one here in the sense? If I would construct one particular logic here, this logic will be this one here. So this is my logic, exclusive OR. One of the inputs might be B. Second input is always 1, for example. Second input is always 1. But first input will be B. Second input is always 1. So look at this 1. So exclusive OR of 1 will be equal to 0. If you observe, so exclusive OR operation. So A, B, and A exclusive OR of B. A exclusive OR of B will be taken. If you take something like this, 0, 0, answer will be 0, 0, 1, answer will be 1, 1, 0, so answer will be 0, sorry, 1, I'm sorry, this is 1. So 1, 1, answer will be 0. Look at this, 1 exclusive OR of 1, this particular case will be 0. So B value will be, now let me take another color, B value will be equal to 1, then 1 exclusive OR of second input is always 1. 1 exclusive OR of 1 will be 0. Now, B value will be equal to 0. Let me take some other color. B value will be equal to 0. Okay, B value will be equal to 0. So, second input is always 1. So 1 exclusive OR of so 0 will be equal to 1. So, this is the case. Either this case or this case. You can take any case. Okay, these two cases will be applicable for B equal to 0. Okay, like this, using this exclusive OR operation, you can apply the 1's complement. I am talking about only 1's complement. I am talking about only ones complement, and this ones complement will be added with 1, then that will be considered as two's complement here. Please memorize, this diagram for a while. How could I change this particular diagram into some other way? Please memorize it. Please memorize it. Okay, please memorize it for a while, and then I shall draw. If you memorize this particular diagram, then I shall draw in a proper way. Okay, let me draw this one. Probably it is there with you in your notes. I think during my explanation you may be draw. So look at this. This is my full adder. This is my full adder. So however, if you are able to draw, I mean I add 2 bits, 3 bits, you need to have a full adder here. This is my full adder not. And let me copy this one and paste for 4 times. For example, if you are trying to construct only, so 4 different types of bits only. So again and again. So let me take this one here. Let me take this one here. So for example, these are the proper bits here. Let me consider this one here. Okay. So now, how could you make this particular thing as possible here is in 4-bit positive adders. In 4-bit positive adders, so input of C0 input is always equal to 1. That's what I have told you. C0 input is always equal to 1 here. That's what 0 here. That's what I told you. Now you can consider how this could be make as the same circuit. How could you make this one as a subtractor here in the sense A will be same. There is no difference while talking something about A here. A will be taken same, that is A0. There is no difference. But while taking B0, so you have to draw one small diagram here that is called as this is B0 actually. As I told you, second input of that particular gate will be always 1. Let me draw some other time. Wait for a while. I would like to draw that particular thing after some other time. So let me copy this one for a while. Okay, because I could not able to draw for number of times. So this is B here. This is again B here. This is again B here. This is again B here, because I could not able to draw for number of times. So that is why I have copied. That's the only reason. Okay, so this is B1, this is B2, and this is B3. So of course, A2, A1, A2, and A3 will be same. A1, A2, A3 will be same here. Okay, so now look at this. So how this could be converted? So here it is B1, here it is B1, here it is B2, and here it is B3, and this is A1, and this is A2, and this is A3. Let me take one particular input. That input must be always equal to 1. Always equal to 1. So that input, let me consider this input is M. Okay. So consider that this one. Consider that this one. Consider that this one. Always M will be always equal to 1. Now, so if you send so B bit with exclusive OR by taking one of the inputs must be always equal to 1 will be always finds the ones complement. Then by adding 1 to that particular thing, then that will be considered as 2's complement. So therefore, default input for the first bit full adder C0 will be taken as 1 here. So whatever the M you are supposed to take, that will be added to this one here. And of course, one sum will be there. This is S0, and this is S1, and this is S2, and this is S3, and finally this particular thing will be so carry 4. And you need to eliminate this carry 4 for a while, because carry 4 value will be always making sense for adding negative sign or not. However, outcome of this particular FA naught will be, and of course this is FA1, this is FA2 have copied so that everything will be seems as it is. So this will be, so C1, and this will be C2, carry will be goes for this particular thing, and this will be C3, and finally you got this one here. Okay, so this is the way you have to draw the logic diagram for, so 4-bit subtractor, 4-bit subtractor, and of course it could be taken in terms of adder and subtractor as well. Okay, something like this. So one of the bits must be always flipped. That flipping operation will be done by the exclusive OR gate. By the exclusive OR gate, you can perform this one. So while explaining this one, you need to always take care about C4. If C4 will be equal to 1, so excluding C4, so S3, so S2, S1 and S0 will be the answer. That is the answer. Of course, before this, there is a plus sign. Of course, if you are not supposed to give any plus sign, then that will be considered as, so plus only. If C4 bit will be, let me drag some more. Okay. If C4 bit will be equal to 0, then what you are supposed to do here is find the, so find 2's complement of find the 2's complement of this particular thing. What is this? So S3, S2, S1 and S0, and put second thing. First one is this one. If C4 equal to 1, second operation will be, so put negative sign before that, before the 2's complement of before the output of first step, before, so output of first step. Okay, so if C4 will be equal to 0, then you have to do these two operations. If C4 will be equal to 1, okay, whatever the answer you have to consider here on excluding of C4. Here also you need to exclude this particular C4, but if it is 0, you need to do this. If it is 1, no need to do anything here. That is final answer. In this way, you could perform. So this, okay. So this is what about the complete information regarding to adders. Of course, adder, subtractor, so half adder, full adder, then 4-bit adder, direct adder, and 4-bit adder, subtractor. 4-bit adder, subtractor. Something like this. Okay. So this is what about our complete information regarding to so what is that? Multi-bit adder. I have given subtractor as well. Tomorrow we will finish off this particular these two operations. Okay, these two operations, multiplexers and demultiplexers, as well as the decoders. If you finish off by tomorrow, then we'll finish off. So understanding of sequential circuits is very important, because so sequential circuits will be play a vital, very much vital role in logic circuits, because random access memory, readable memory are being, or any full-fledged transistors are being, I mean ICs, integrated circuits are being constructed with sequential circuits only. Okay, sequential circuits only. So therefore, tomorrow we shall finish up this particular these three topics, and then day after tomorrow we'll go for this particular complete sequential circuits. Then unit 2 will be gets completed. I think yes, unit 2 will be gets completed by day after tomorrow. Okay, that is what the full-fledged information to you. So you please go through once.